Okay, so in the last video, we saw that we could define this rotational kinetic energy for an object that is rotating or rolling. So we can define this quantity. What we want to think about next is use the simulation to help us determine a trend of what we're seeing. So what I did was, here's the rotational inertias, or sorry, the moments of inertias for all of these objects. We said again that different objects have different moments of inertia based on their distribution of their mass and where that mass is and what shape of the mass it has. So I took the liberty, I'm not good at thinking in fractions, so I just turned these fractions into decimals. So we have 2/3, so 0.666. We have 2/5, so 0.4. We have 1, and then we have 1/2. And we're going to assume that they have the same mass and the same radius. So m and r are the same. So really the main thing that's changing the moments of inertia is just that fraction out in front of them. So what I want to do quickly is just rank our moments of inertia from highest to lowest, just to help us think about it and kind of visualize this. So we have the shell or the cylinder. So the cylindrical shell is greater than the spherical shell. SPHSHELL, which is then greater than the solid cylinder, SOL-CYL, and then which is greater than the solid sphere, solid sphere. And now what we can do is check to see, so we've kind of ranked our moments of inertia. So I rankings. We've ranked our moments of inertia, and now we can rank what order we see these things coming into place and see if we notice any trends, any similarities. So for ranking the placement of these things, like which order they reach the bottom of the hill, first we have the sphere. Then we have, it looks like, our solid cylinder. Then it looks like we have our spherical shell, which is just kind of like a ball, right? Like where it's no mass in the middle, all the mass is on the outside. And then our cylindrical shell. So we notice a trend. Looks like we can say the greater the moment of inertia, the slower they're going. So if I is greater, it looks like our V is less. It looks like they have less kinetic energy. They're reaching the hill in a shorter amount of time. We said in this first case, this thing was getting, the cube was getting all translational kinetic energy. So that was all going to the velocity, and that made it move quicker. And when we analyzed the sphere, some of the energy, the gravitational potential energy, was being turned into rotational kinetic energy. So it was getting less of our translational kinetic energy. So that kind of helps us see if we have more rotational kinetic energy, then we have less kinetic translational energy. So the more rotational we have, the less translational we have. And that fits in with what we know about our LOL diagrams. If we have more rotational, then we have to have less of our translational in order to make that work out. So we can kind of develop a trend. We can say the greater our rotational inertia, the greater our rotational kinetic energy is. And that is based on that reasoning that if we have a greater moment of inertia, it means that our object is moving slower, right? No, the other way around. If we have a greater moment of inertia, we have less velocity, less translational kinetic energy.